and I will also I can also save the whiteboard to make sure I can just send that out as a PDF later.
Okay, cool. Thank you.
So the limit as, let's say limit as x approaches a of f of x equals L. And the limit is x approaches a of g of x equals capital M. The good news about these limit laws is that they act largely, intuitively. And just to kind of illustrate that, what if I give you this? The limit as x approaches a of this new function, 3f of x minus 2 times g of x. I mean, we can kind of break this down. So I know that my limit as x approaches a of f of x is L. So I mean, I could prove this for you. I don't know if that's the best use of our time, but if I triple the function and look at the same limit to the same base point, I should get triple whatever that limit was. And kind of corresponds on the for g, if I double g, I should get double that limit. And if I make a function by taking the difference of those two things, my limit is going to be the difference of those two limits.
Okay, so it's just like basic addition subtraction for that.
Yeah, so I mean, basically what the limits laws say, and I would encourage you to go to Canvas and find the slides for this. I think it'll be chapter 1, probably 1.4 or 1.5.
Yeah, it's 1.4.
1.4, okay. But all these are in there. And yeah, basically, sums and differences, behave in the way you would expect them to. Scalar, like constant multiples, like we saw here, behave in the way you expect them to. Products, so like if I had this, limit as x approaches a of, -2 f of x g of x. That would be equal to -2 LM. Differences get a little weird, or not differences, quotients. So what if I had the limit of x approaches a of this f of x over g of x? What would that be? What would that limit be equal to?
Would it be L over M?
L over M. What's the only danger?
If the limit of g of x is undefined or non-existent?
So I'm telling you that both these limits exist. So these limits exist and they're real numbers. But even though they both exist, there's still a danger. And that danger is, what if M is equal to 0?
Oh, so, then the whole thing is undefined.
Yeah, then so even though the two individual limits exist, that quotient
it can still be undefined itself.
Right, so,
okay, got it.
So that's the only caveat on the quotient there. And I think there were the other laws I gave you were like compositions of functions and powers and roots. But the good news is they all largely act like you would expect.
Okay.
But in
sorry, quick question about them. So I feel like since we've learned the limit laws, we've also learned like other stuff that help calculate limits like more efficiently. So when exactly would you use limit laws over something else?
So, and here's kind of the bad news about how intuitive they are. You've probably been using them, without really even thinking about it. And I'll give you an example. Okay. So if I give you the limit as x approaches 2 of x squared plus x minus 6 over x squared minus 4. So clearly you can't just evaluate this where x equals 2. But if you do some factoring, you get, I think it's x minus 2, x plus 3 over x minus 2, x plus 2. And this is kind of a simple case, but when we get to this last step here, you really are making use of the limit laws because, well, maybe I should not take that for granted. So now that I'm here, do you know what the limit's going to be?
Is it 5/4?
5/4, yeah. So, and you just kind of evaluate that by looking at it, but really what you have to know is that, all right, does the limit of that numerator exist? Yes. Does the limit of that denominator exist? Yes. Is the limit of the denominator something other than 0? Yes. Okay, then I can strictly just divide.
Oh, so it's basically like I can just look at it and evaluate it because
Yeah.
those laws exist.
Right. Yeah. I
Okay.
mean,
So it
that's
just
why we can do
allows
them.
that to happen.
Yeah. So I mean,
Okay.
if this was like an advanced calculus class, we would have proved every single one of those things. But they really are very intuitive and to the point where, you didn't even realize that you've been using them when you've needed them.
Gotcha. Thank you.
Yeah, no problem. All right. Alexander, you have any questions?
Not really. No questions in particular, but other than like the exam itself. So like for like what percentage would you say of the exam being limits and then derivatives as well as like word problems?
I would definitely expect to see all of those things.
Yeah.
I mean, obviously you're going to see limits and derivatives. That's all we've talked about so
Yeah.
far. And really, and technically, limit drives all of that stuff.
Okay.
You are going to see some word problems, but really, kind of weird way to answer that question, but I'll say this: if I had half an hour to study for this test,
Yep.
I would be really, really comfortable with what a derivative told me.
Gotcha.
Basically, and we've talked about a few of those different things, like, what are all the things the derivative tells you? What does it tell you about the function when you take a derivative? Because if you really understand that pretty well, I should be able to give you some strange situation with some mathematical model. And if you understand what the derivative is telling you, you should just be able to find it and use it.
Okay.
And I think somewhere on the web work, probably pretty recently, actually, I'm pretty sure there were some questions like that where you have to, you basically have to apply differentiation to some strange looking function or some strange situation. If I'm wrong about that, I know there are some in the practice problems that I put on Canvas that are in the textbook.
Gotcha. I'll look into that. So thank you.
No problem. All right, Luca.
I wanted to ask, how hard do you think the homework is compared to the test, like the homework problems?
It's a tough question for me to answer, but typically the homework is harder than the test. I mean, when I say typically, I mean in pretty much every math class I've taken, and probably most of the ones you've taken. And at least that's my aim. Is that the homework is kind of is more difficult than what the test is, because for the homework you have a lot more time and you can use whatever resources you can get your hands on, where the test is going to be approximately 50 minutes and you're on your own. So one piece of advice I'll give, and this is in general, is, you know, go back and look at some of the things you've done on the homeworks and done on the quizzes, and in some cases redo those questions. And even though you've already done them, that doesn't mean you necessarily remember all the ins and outs or why you had to do the things you did. So I would yeah, I would encourage going back over that stuff and making sure that, you know, you still understand what's going on and you can still do it. All right. Thomas, you have anything?
I don't really have a question for the exam as much as I do just for me taking it in general.
Yeah.
Because of my like skin that's going on, I'm not going to be able to come to class on Wednesday. I think we have the test.
Okay.
Am I still going to be able to take it on Wednesday?
Let me find out. Yeah, let me get ahead with you. Let me get in touch with you one-on-one.
Okay.
Because I wasn't aware that you weren't gonna be able to come to class that day, so I'll have to look into that.
Okay. No problem.
And my short answer is almost certainly yes. We'll figure it out for Wednesday. I just
Okay,
have to figure
cool.
out what that looks like.
No worries.
All right, and then I think Alexander. Do you have anything?
No, I'm good here. Thank you.
Okay. Then I think, am I still showing my whiteboard? Lost it. No, it is.
No.
Gabby, do you have any questions?
Just the exam was from 1.3 to 2.3, right?
Correct.
Okay, that was it. Thank you.
Okay. And then Sal, you just joined. You have any questions? All right, I think we're back to the. All right, Jonathan, I think we're back to you.
Okay. Let me see. Let me check my notes and see what else I need.
Okay.
With you in like I'll be back in like 2 minutes. Okay.
Okay. All right, Cameron.
Yeah, so I was hoping to go over squeeze theorem next.
All right, right. Okay.
Yeah.
Do you have an example you want me to look at?
Yeah, so just looking at the one from quiz number 1,
Okay.
I'm just going to use this example. So
Okay.
it says the limit as x approaches 0 of x squared times cosine of 1 over the absolute value of x.
Okay. All right. So definitely recognize it as a squeeze theorem example. So what do we need to make the squeeze theorem work?
Is it the maximum and minimum of cosine?
Yeah, so part of what we need to do is, one thing I know about cosine of x is that it has bounds above and below. So it's never less than -1, never greater than 1, right?
Yes.
So, and here's the nice thing about that, I can say the same thing about, and really, I mean, I threw this weird thing that's cosine of 1 over the absolute value of x, but really
Yeah.
it does not matter. I mean, it's still bounded.
Okay.
So
And is
this
that
right,
just because of it's still bounded in between -1 and 1 because of that cosine function right there?
yeah. So I mean,
Okay.
if you think about what 1 over the absolute value of x does, you know, let me just draw a quick sketch of what it looks like. This, it's going to look a little bit like your 1 over x graph, except it's just never going to be negative.
Okay.
So it's a little easier to think about what happens as you get really far away from the y-axis. If I go very far to the right, then my x values are getting really, really small,
Mm-hmm.
which means, 1 over x is getting, I'm sorry, 1 over x is getting very, very small. So basically this thing right here, this cosine, is approaching cosine of 0.
Okay.
So it's approaching 1, which is fine. Same thing for the other side. And as you get closer and closer to the y-axis, then basically, this 1 over absolute value of x is getting bigger and bigger and bigger. But all that's going to make the cosine function do is just, oscillate up and down faster and faster.
Okay.
But it's never going to give you a value that's less than -1 or greater than 1. So,
Okay.
no matter how weird that argument to that cosine function is, you're
always-
bounded between -1 and 1.
Okay. And so it doesn't matter whatever's inside the parentheses after cosine?
Right.
Okay.
I mean, as long as it's well defined.
Okay.
Really, and cosine always is.
All right.
So now that we got that, what else do we need to make the squeeze theorem work?
You multiply the maximum minimum by x squared, right?
There you go. So yeah, I'm going to multiply all 3 branches of this by x squared, and I get this: -x squared is less than or equal to x squared cosine of 1 over absolute value x, which is less than or equal to x squared. So what I have basically is this. And I think the way I presented this class where these functions were called f, g, and h. The least was called f, the greatest was called h, and the one in the middle, the one I actually care about, is g, right?
Mhm.
Which is so then what?
This is where I'm not sure. I think you
Okay.
graph the minimum and the maximum. So f of h, or I'm sorry, f of x and h of x. And then from there you can figure out what g of x looks like.
You actually don't. I mean, I graphed it in class, but you really
But that was
don't.
just like a demonstration.
Yeah, just to show
Okay.
you
Well,
kind of
then-
how it works. But basically, I guess before we go any further, I should make sure of this. Do you agree that this is going to be true for any value of x?
Yes.
Okay. Didn't sound quite so sure, but I'll
Yeah.
So, and really, maybe we need to back up a step. Are you convinced that this thing right here is always true?
Oh, yeah. And then so if you multiply all of it by the same
Right.
thing, then
All I did was multiply everything by the same thing. So if we're okay with this, this string of inequalities always being true, so I know that the far left side of this is always going to be the least. I know the far right side of this is always going to be the greatest. The middle is always going to be somewhere in between them. They might be equal, but they're always going to be in between. So what the squeeze theorem allows me to do is this. I can take the limit as x approaches 0 of either of the two. So of the least of those 3 functions and of the greatest of those 3 functions. And what are those limits equal to?
I think the first one is 0, and I think they're both 0.
Yeah, they're both 0.
Okay.
So, and we've already convinced ourselves that the one on the left, -x squared, is always less than or equal to +x squared, right?
Yeah.
So if they're the same as each other, and I know I have a function that's in between them, then that means that the limit of the middle one has to be 0 as well.
Okay.
Therefore, so that's how the squeeze theorem works. It's kind of, it's kind of a strange thing. And yeah, the graph makes it a little easier to see, but basically the main, the kind of the rationale behind it is, all right, I found a minimum and I found a maximum. If I can get that minimum and maximum really, really close together, then anything between them I know is very, very close to that minimum and that maximum. So if I can get them on top of each other, in this case, they have the same limit, then the middle must have the same limit as well.
Okay, thank you.
No problem. All right. Who was after Cameron? I think it was Luca.
Oh, if it's me, I was gonna ask about the tangent lines and normal lines.
You got a specific example you want to look at?
Can we do one from the homework?
Sure.
It's asked for the tangent normal lines at y equals 5 plus 4x squared at the point 3 and then 289.
3 and 289, 289.
Yeah.
It's 5 plus 4x squared.
5 plus 4x and then all that squared.
Oh, okay.
Yeah, my bad.
Okay, that makes sense. Okay. All right, so I want tangent line and normal line. So if I want to, let's just do tangent line first. If I want to find the equation of the tangent line, how do I start?
Would you start by finding the derivative of the equation?
Yep. So what's that derivative going to be?
Well, I use the chain rule. Let me find the paper. I think it's just 8 and then 5 plus 4x.
Okay.
In 5 plus 4x in parentheses.
Yep. So if not everyone here knows the chain rule, that's fine. We'll get into it after the test, but another way you can do this is just by expanding this, so y equals 25 plus 2 times 4 times 4, 40x plus 16x squared. And you can take the derivative of that, which comes out to 40 plus 32x, which is the same thing we're going to get here. All right, so we got the derivative. Now what do I do with it?
Find the slope or something like that.
Okay. How do I find the slope?
Would we plug 1 in?
Y1.
No idea.
Okay, so I want to find the tangent line. So the derivative, so y, this y right here, this y is a function of x, the one you gave me. The derivative is also a function of x. So in order to find, so that derivative describes the slope of the curve or the slope of the tangent line, you know, wherever I want. But now I have to know, I have to have a location, a specific x value to get something specific, to get an actual number for a slope. So where do I care about, like, where do I want this tangent line to be? Where do I want it to intersect the curve? So if I'm graphing this function, it's going to be a parabola. I think it's going to look something like this, where it just touches the x-axis. So I'm going to have something like this. I'm going to have a tangent line here. So that tangent line only touches this parabola at one point. That's this point right here. But I can draw that tangent line so where it touches that parabola anywhere. But I only care about one place. What are the coordinates of that point that I really care about?
3 and 289.
Right. So that's the point I care about. So what x value do I need to evaluate my derivative at?
3.
So that'll give me this slope 40 plus 32 times 3, which I think is 136. All right, so now I have the slope of the tangent line. How
Wait,
do I,
136 is the slope?
or do you understand why?
Yeah, I think so now.
So yeah, that's the slope of the tangent line, because that's, think about what the derivative means. The derivative is the instantaneous rate of change of the curve at any point. It gives you the slope of the curve. So, and just to be really clear about this, when I draw a tangent line to a curve at a certain point, at that point, that line and the curve have the same slope. So this slope of 136, the curve, the parabola has that slope at that point, and so does that line. That line has that slope everywhere because it's a line. So now how do I find the rest of that equation?
You can plug in 289 as y and 3 as x.
Into what? Plug that into what?
We can do like point slope formula.
Point slope? Okay. So yeah, I know that y1 is 289. Yeah, if you want to leave it in point slope form, I think web work is okay with that. That should be good. You okay with that?
Yeah.
Then you also ask about the normal line. So what's the normal line? Do you know what that term means?
No.
So we've done an example or two of this in class, but basically normal line is perpendicular to tangent. So knowing that the normal line is perpendicular to the tangent, and I know what the slope of the tangent line was, what's the slope of the normal line going to be?
It's gonna be the opposite reciprocal of the slope, right?
Right, so what would that be?
Negative 1 over 136.
So negative 1 over 136. And then it's the same kind of thing. And you can use point slope form again. So y minus 289 equals negative 1 over 136 times x minus 3. If you were to simplify that out to slope-intercept form, you would get wildly different y-intercepts, but that's okay. Yeah, that's how the tangent line is related to the normal line. They're just they're perpendicular to each other.
Okay.
All right. Tal, do you have anything? How about Thomas?
I'm just sort of watching.
Okay.
But I did have a question. Someone already asked this, but I didn't hear. What sections is the test on?
From 1.3 up to 2.3.
1.3 up to 2.3?
Yep.
Perfect. Thank you.
Sorry, I just grabbed my mic.
Oh, no worries.
So yeah, I'm just here also watching just to make sure I have everything down.
Okay.
Uh,
All right. Who else?
I do actually have a question now if no one else does and if I was next.
Yeah, go for it.
Okay. So I had a question regarding quiz 1. Question 3 using the intermediate value theorem.
Okay.
So I was kind of confused on how much like the interval size that you needed, because on the problem 3a it says one of the answers could be 3.8, but I thought you wanted it smaller than that, and I was wondering how small you wanted it to be, like, and then
Sure. So remind me what the question is, or yeah, I know it's about the intermediate value theorem, but what are the details?
let me pull up the actual quiz itself because I have the quiz solution up right now. Sorry, give me a sec.
Oh, that's okay. I have it now. So function is x squared plus x. X squared plus x over x minus 1 on what interval? 3.8. Okay, so here's the function. There's the interval. What am I trying to show you? Use the intermediate value theorem to show that for some value c, f of c equals 15/2, and then give that interval.
And the answer that you gave on there was 3.8, which is the same, which basically it tells you that in the problem. So I was just wondering.
So it's not exactly the same. So let's go to the intermediate value theorem piece by piece. So what does the theorem say?
That the a number c must be between some interval between a and b. I'll call it, I guess.
Okay, so there's some stuff that I have to satisfy before that. So I'll just do them in bullet points here. So I want to suppose f is continuous on some closed interval AB. All right, so let's make sure we have that. This function f, this x squared plus x over x minus 1, is that continuous on my interval 3.8?
Yeah, it is.
How do we know?
Can't you just take the derivative of it?
No, the derivative doesn't
Or you'd plug it in, right?
Plug what in?
3 and 8 into the equation.
So that would tell you that it's continuous at 3 and at 8, but it might be discontinuous somewhere in between there. So let me ask it this way. Where would this function not be continuous?
Oh, 1.
At only 1, right?
Right.
So the only x value where this function would be discontinuous is outside my interval. And since this function is a rational function, I know that it's continuous everywhere where it's defined. So we're okay there.
Gotcha.
What else do we have to have? We have that f of 3. Sorry, I'll use the general. I have to have that f of a is different from f of b. Do I have that? Well, let's see. What's f of 3?
9 plus 6.
So f of 3 is 6, and f of 8 is
72 over 7.
72 over 7. Okay. So we have that. They're definitely different. I am trying to show that for some value c, f of c is equal to 15 halves. How do I know that has to be true?
I don't know.
Okay. So, and this basically, this next part is why this theorem is called the intermediate value theorem. So these two are the things I have to satisfy.
Oh, wait. It's because it's between 6 and 70. Is it because it's between 6 and 72.7, right?
That's exactly it. So
Gotcha.
then for all n, and n is just some number between f of a and f of b. So in this case, our n is 15 halves.
Right.
So for all n between those two numbers, there is a c on this interval, and it's not exactly the same. This is dirty, there's trash. So there's a c on the open interval, and the big difference there is that, you know, there's some c where f of c is equal to 15 halves. And it's going to be strictly between 3 and 8. And what I mean by strictly between is it'll be bigger than 3 and less than 8. Let's turn it back on. Does he turn it back on? All right, so there is a c on this interval. So basically that's how we show that. So intermediate value theorem, we satisfied all of the conditions of the intermediate value theorem. That's why we get to say this. So we have f of c equals 15 halves for some c, and that c is somewhere on this interval.
Right.
Bigger than 3, less than 8.
Okay, that makes sense.
So that was part A. And then since part A, you proved that that thing exists. And then for part B, I just want you to find it. Did you need to go through part B or just the first part?
If we could just go through part B really quickly.
Yep.
So it looks like you cross multiplied on B.
I may have. So I don't remember exactly how I did the solution, but thanks to part A, I know this is true. f of c is equal to 15 halves. And really f of c is just equal to this, c squared plus c over c minus 1, and then yeah, I probably cross multiplied.
Okay.
So 15 times c minus 1 equals 2 times c squared plus c. 2c squared minus 13c plus 15 equals 0. Okay, yeah, I think that looks good. And then let's just go ahead and skip forward to Mo. What did I get for C if you're looking at the solution still?
We ended up with 3/2 and then 5, and then you got 5. And I'm guessing you 3/2 you didn't put that one because that one is outside of 3 and 8, correct?
There you go. So yeah, the value that I get, so the value guaranteed by the theorem is between 3 and 8. So this 3 halves, that 3 halves is not guaranteed. I mean, it's fine that it exists, but it, you know, for some other example, you might not get things outside of that interval. So that's why 5 is the only one that's guaranteed by the theorem.
And so just wondering, so if you didn't have a fraction and then you just had a 7, you can plug it into the C's, right? You don't have to multiply 7 by C plus 1 and whatnot. You can just plug it in, right?
No. So think about what C is. So what kind of a value is C?
The value you're looking for?
Right, but like, is it an X value? Is it a Y value?
It's a Y value. I mean, X value.
Yeah, C is an X value. So, you know, basically what you're suggesting is that I think your hypothetical here was that you said, okay, what if it was, instead of 15 halves, it was just 7?
Yeah.
Well, in that case, 7 would be a Y value.
Right.
So I don't want to plug that Y value of 7 in for C, which is an X value.
Okay. So then you just do, say, C or 7 times C to the second plus C, and then C or 7 times C plus 1.
Basically, the bottom line is that, you know, so I could have asked this question I could have replaced 15 halves with 7, right?
Right.
And the theorem would still give that to you. Wouldn't give you a C value as nice as 5, but you would still be able to find one. But let's say that you had f of C equals 7. Then basically what you're going to do is this. 7 equals C squared plus C over C minus 1. And then you're solving that equation.
Gotcha.
So basically, yeah, part A of that question was you're showing me why the intermediate value theorem can even tell you something. And then for part B, you're trying to show me the exact thing that you proved existed.
So then so if I'm correct, you just multiply the C minus 1 over the 7, and then subtract the rest, or add the rest on either side, whatever.
Yeah, basically you're going to have a quadratic formula or quadratic equation that.
Okay, I got it now.
It won't factor, but it can definitely be solved.
Yeah. Okay, cool.
Oh. All right. What now?
If nobody else has a question, I have a question about the test.
Sure.
So are graphing calculators allowed, and do you think we'd even be needing to use them?
They're absolutely allowed. I would definitely bring one if you have. I mean, hopefully you have one you can use.
Right.
But yeah, I mean, I'll remind you of the same stipulations I gave on the first day, as long as they're not the sort of calculator that can solve algebraic equations
Right.
immediately. So, you know, if I see the three letters CAS on your calculator, I'm probably not going to let you use it. But I think you and I talked day one, and I think you're okay.
Okay. Thank you. I thought so. I just
I
wanted to
think
make
you're,
sure.
yeah. I mean, so you know, most of the TI calculators are fine. The two really notable exceptions are, I remember the one that was new when I took high school math or calculus was the TI 92, and I don't even know if they make those anymore. But some of the new TI Inspires, not all of them, have that computer algebra system on there. But I by no means do all of them have that.
Okay. I just wanted to make sure I could bring it.
Yeah, and any of you, if you have any doubts about whether your calculator is okay, just send me a picture or send me the model number and I'll tell you for sure. But yeah,
For the Inspires, it's just if they have the CAS on the top instead of the CX.
correct. Yeah, CX.
Okay,
I'm not sure what the CX package is, but I don't think it.
I think the CX is just the normal one.
Okay. Yeah, so I looked up the Inspire CX, and the first match I got was, is it allowed on the SAT, which is kind of the same benchmark I use. Because it's all the CAS ones are banned from, you know, those standardized tests for the same reasons that I would not like them, is just because they do the algebra for you, which is not something we're going to take. Anything else?
Yeah, could you go over one of the questions on the second quiz?
Yeah, which one?
The difference quotient, number two.
Remind me what the
Yeah.
function was.
The function is g of x equals 1 over square root of x.
Okay. All right, so I want to find the derivative using the difference quotient. So g of x plus h minus g of x over h. Okay, so 1 over a radical x plus h minus 1 over radical x all over h. All right, I'll go ahead and take some inputs for the rest of this. Where should I go from here?
You should probably get the same denominators for both your fractions and your numerator. So you would
Okay.
multiply one side by radical x or square root of x. So the left side, you would multiply that. And then on your right side, you would multiply square root of x plus h to get the same denominator.
Okay. So doing that through would give me radical x minus radical x plus h all over radical x plus h all over h. Good move. Now what?
Would you multiply by the conjugate for this one?
I think so.
So what you would do is you would multiply, so you just change the signs of like the top fraction. So you just multiply that, both the numerator and denominator, except that it would be square root of x plus square root of x plus h. Does that make sense? To both sides. Yeah, it would be for both the numerator and denominator. You'd be multiplying, it'd be the same. Okay.
All right, so doing that, So the whole purpose of the conjugate is to clear those radicals.
Yeah.
So that numerator is going to become x minus x plus h all over. This remained unaltered. All right.
Yeah, and
Now-
then this part I got kind of confused.
Okay.
Yeah.
So from here, I mean, compound fractions are kind of a nightmare.
Yeah.
So especially when there's like an odd number of branches like this. So maybe it'd be more digestible if we did that and really made it obvious that I have a fraction within a fraction. And
Yeah.
so if I have that, then really what I can do is this. I can clear this nastiness with a compound fraction by multiplying both numerator and denominator by 1 over h times radical x plus radical x plus h.
Okay.
It has the benefit of canceling all of this entirely.
Mhm.
All right, so the limit as h approaches 0 of
So does the x's cancel out, obviously, right? So then we
these
left with-
x's cancel, and then I'm left with negative h.
okay,
So
the negative, gotcha.
so now that's going to leave me this negative 1 over radical x plus h times radical x plus radical x plus h. All right. So now what can I do with this?
So you can distribute here, and then eventually you'll plug in the 0, but not yet. I think what you do, you distribute and you get square root of x times square root of x, which equals x. And then I suppose you could do that with square root of x plus h, but then you could probably do 2 moves in one and plug in 0, maybe.
So yeah, I mean that's what I would suggest. You could absolutely distribute now,
Yeah.
but it's gonna be a little strange. The good news, I mean, it wouldn't be wrong, but it would be, I think, hard to keep track of all those moving
Gotcha.
parts.
Okay.
The good news is that you can absolutely evaluate this limit now.
Mhm.
So doing that, you get negative 1 over, and I'll just radical x times radical x plus radical x. So hopefully that, now that we've evaluated the limit, this just becomes easier to deal with.
Okay.
I'll try to take this slow. Radical x times radical x becomes x.
Yeah.
The parentheses becomes 2 radical x. And then I saw lots of different ways this looks, but we'll just keep it like this.
Okay. And that's our answer.
Yeah.
Awesome. Okay.
I mean,
and yeah,
there
yeah.
are other ways to express this that are also correct, but that's fine.
Okay, sweet. And then for part B, it asks for find the equations in the line tangent to the graph of f at the point where x equals 1 over 4. So would you just plug in 1 over 4 for that? Because we found the derivative right there.
Yeah.
So okay, just plug in 1 quarter into x.
Yep. Mhm.
Gotcha. Okay, thank you.
Yeah, no problem.
I had a quick question regarding taking the derivative. So are there going to be some questions on the test where it asks you specifically, I want this type of rule used?
in general, be ready for that. But kind of like I explained today, like all the different differentiation rules, they're just tools. It's up to you kind of decide when they're most usable. For example, if I gave you this function here,
You just
I could differentiate this by using the product rule. But why would you? So the one thing I will tell you to be prepared for is, all these different differentiation rules we've gone over, like in the last couple of sections of chapter 2. These are kind of downstream of the difference quotient. So definitely be ready for me to require the difference quotient of you. But as far as the other rules, it's, one of the big things that we need you all to understand and get some practice with and master is how to use differentiation and when to use certain differentiation techniques. So aside from the difference quotient, I don't foresee me requiring you to use any particular rule.
Okay, because I know there was one on the homework. I think it was 2.2 or maybe 2.3, but I solved it using the power rule. But there was a part of it that asked, like, what is A, and then you had to use the difference quotient. So
yeah, I remember. I think that we talked about that one specifically, but yeah, that was why you missed that part. Anybody else?
Will there be any more of these before the test?
Unfortunately, no. I mean, so I'll have regular office hours tomorrow between 3 and 4.
All right.
On Zoom. But I'm not going to be able to have another one in the evening. Having said that, if you have any questions, you can either email me or post something to the ed discussion on Canvas, or kind of one of the benefits of you being in 265. There are probably 20 or 30 sections of 265 running right now, which means pretty much every tutoring center on campus will have somebody who can help you. So I think the address is tutoring.asu.edu. Let me make sure that I am remembering that right. Yeah, tutoring.asu.edu. And a lot of those are on campus. A lot of them are also online. For example, my Tuesday office hours are online. My Friday office hours are in person. So lots and lots of help out there. And I bring that up just to let you know there are other resources, but you can always email me. But yeah, don't cheat yourself by only sticking to one or two avenues to get help.
And your Tuesday office hours is also the same Zoom link, right?
They're not. So that's a good question. So right now, this is my personal Zoom room that I use for like office hours and one-on-one meetings and stuff. But my My online office hours are run through the MCC. So I'll drop that link in chat right now. So I'm going to put this link in chat. This is just for the MCC, the Math Community Center in general. But if you go there, like if you go to that link, it'll show you the schedule, like, and really if you go open up the schedule, it'll show you when every single one of us, all the TAs are working and when we're there. But also on that page, you'll find the link for the Zoom based office hours that are from 3 to 5 on Monday, 3 to 5, Monday through Thursday. Again, you know, because Math 265 is such a, I mean, there's so many of you taking it, you know, everybody in the MCC, either on Zoom or in person, can answer your questions about Calc 1. So my office hours are from 3 to 4 tomorrow, but you can always, I would encourage you to call in or go to the MCC at any time. Somebody can always help you.
Would it be all right if I asked a slightly less relevant question?
Of course.
It's still related to the course, but it's section 2.4 homework.
Oh, okay.
It was the last question, problem 15.
Okay.
The last part of it, it asks for the distance in centimeters. How far from its equilibrium position does the mass travel? But I'm not exactly sure what it's asking us to calculate. Is it
Okay.
asking us for a function like at seconds essentially? Or is it?
Do you want to share your screen? Because
Sure.
a lot of these questions are randomly generated. So
Yeah.
if I pull it up, I might have different numbers to look at. So let me stop sharing.
So essentially right here, it asks how far is it from its equilibrium position does the mass travel?
Okay.
But I'm not entirely sure like what it's asking for, like what time, because obviously when the mass passes through the equilibrium position for the first time, it's like at its amplitude. But when I input that, it didn't give me the correct, or it didn't register that as being
Okay.
correct.
So an elastic band is hung on a hook. The mass is pulled downward and released. It vibrates vertically. Equation of motion is that, where S is measured in centimeters. I assume the equilibrium position is where S equals 0.
Yeah.
Okay.
Well, it's where actually I think it's where the velocity is equal to 0.
Oh, that makes sense. Okay. So you found where velocity is equal to 0, right?
Yes.
That's 2.55, and that was correct.
Yes.
Okay. So you found the time when the mass reaches that equilibrium position, right?
Yeah.
But you have not yet found what the equilibrium position is.
Got it. Okay, so I'm assuming we just plug this back into the actual function S of t.
Yes.
Oh, I think I know what I
in
did
part.
wrong.
So if you plug that time value into to S of t,
Yeah.
that'll give you the equilibrium position. And then I think you will still need to figure out like how far away that position is from either the minimum or the maximum
Got it,
of this
which
function.
should be just in general 0, right? Or well,
I don't
is
think
it
it'll be 0.
no, okay, got it. That's where I went wrong.
Okay.
Okay, thank you so much.
No problem. Anybody else have anything? All right, I'll go ahead and stay online for the next 15 minutes if anybody has anything.
Wait, this tutoring session is recorded, right?
Yeah, I'll post the recording.
All right, all
Um,
right, thanks. Yeah, I meant you covered the first quiz, question number 3, but I only came in through the middle of it, so I wasn't
Okay. Yeah,
able
you'll
to see all of it. Yeah,
you'll get the rest of it.
I just watch it later.
Okay.
So I'm just looking around the MCC website right now.
Okay.
And yeah, I found the PDF that basically says everyone's office hours.
Yep.
So but the Zoom link to go into the office hours, is it just the one that says use the Zoom link to log into remote sessions?
Yeah, that's it.
So you said yours is from 3 to 4, so
Mhm.
you guys just switch off and on then all the time, or how does
Yeah,
it?
so the way that the way the Zoom office hours works, there's always going to be a student worker there who basically runs it. Basically, they'll put us into let's say you show up tomorrow to office hours and want to talk to me one-on-one, they'll put us into a breakout room. But yeah, like somebody is always there managing it apart from the TAs.
Okay. And so I'm planning on finishing most, if not all, the practice problems tonight.
Oh wow, okay.
I mean, there's not too many. There's only like what, 30? Probably a little more. I don't know if there's anyone else going to be there tomorrow. If there isn't, can we kind of go over some of the ones I have questions with?
Yeah, absolutely.
Cool.
Sorry, wait, where can we find the practice problems?
On Canvas, let me drop that link.
Okay.
And so I made a module, I think Saturday, called exam 1 prep material or something to that effect. It's underneath like all the PowerPoint slides and recordings and stuff. Exam prep materials.
Okay.
So there's a
I see it
PDF in
now.
there that has a bunch of questions from the book in it.
Thank you so much.
Of course.
Actually, I also had, now I'm thinking about it, I had another question on, I think it was on quiz 2.
Okay.
It was where we had to draw our own graph and you gave us some requirements for it.
Mhm.
Let's see, sorry. I was on quiz 1, I'm pretty sure. Yeah. So.
Yeah, that sounds early.
Anyway, your graph had some, let me see, I'm getting on it right now, 1 sec.
Yeah, can you read me the list of requirements that I threw at you?
Yeah, give me 1 sec. So it had, let me see it right here. So it says, as the limit approaches 0, f of x equals to 4. F is not continuous at x equals 0.
The limit is x. Okay. So this limit is equal to 4, but f is not continuous at x equals 0.
Yeah.
Okay.
And then as the limit, or as x approaches -3, f of x does not exist. And as x approaches 4, f of x is equal to infinity. And then the
Okay.
last one is, as x approaches 2, f of x exists, f of 2 exists, and f is not continuous at x equals 2.
So that limit exists. F of 2 exists. F is not continuous at x equals 2. Okay.
Right.
All right. So I am giving you basically requirements at 3 different x values. So, and just to kind of clarify, there are a few things about this graph that are not negotiable, but really this could look very different from even the way that I did the solution. So I care about x equals 0. I care about what happens at, oh no, it's 4 points. 1, 2, 3. X equals 2, x equals 4. Okay. So let's just kind of handle it piece by piece. I know that the limit as x approaches 0 of the function is equal to 4, right?
Right.
So I know that this function has to do something. Something like that. But it also says that f is not continuous at x equals 0. So what does that mean? The function, what does that mean the graph has to look like where x equals 0?
Gotta have an open hole, right?
Right. So a function is continuous only if the limit at that point is equal to the value of the function. So the only way I could have a limit there and have the function not be continuous is if the function is either not defined there or it's defined elsewhere. So like, for example, I could have this. I could have the 0, 1 as a point on this graph.
Could you, I was trying to think about it. Could you have it so, no. Never mind.
You sure?
Yeah, no, I realized it was wrong before I said it.
Okay. All right, so I think these are okay. So I want the limit as x approaches -3 of this function not to exist. So lots of ways that could happen.
Couldn't you say Going to either infinity or negative infinity.
Yeah, so I might want to do this. That's one way. Here's another way.
Okay.
So I could have the either one of the one-sided limits exists, but they don't agree with each other. So that's another way that limit might not exist. But yeah, like lots of ways that could happen. So now I have the limit as x approaches 4 equals infinity. I should probably deal with what happens around x equals 2. So these last 3 bullets here, the limit as x approaches 2 of f of x exists. F of 2 exists, but f is not continuous at x equals 2.
So then you'd have an open circle on the line and then a closed circle somewhere else on 2, correct?
Yeah, so could I have this?
No.
No. So that limit doesn't exist. I need them to agree. So I have to have, that was a little too wild. So have I done my job, or do I have to make any more changes?
You have to make more changes because f of 2 still does not exist.
Okay, let's do this. I'm gonna make it really close, but it's still not continuous. But now I think I've done all 3 of these for x equals 2.
Right.
So now the last one to deal with is f of x, or the limit as x approaches 4 of f is infinity.
Which that line just straight up takes off.
Yeah, so is that enough?
Yeah. I mean, it looks like, or
I should also have that happening from
oh, okay.
the opposite side. And they both have to increase.
So so when dealing with the infinity, you have to have it look like that.
Yeah, I mean, if I tell you the limit of if I tell you something about the limit of a function, without specifying which side.
Gotcha. Oh, I see.
Yeah,
That makes sense.
Yeah, I'm telling you something about both sides.
Okay. Yeah, that makes sense now.
Yep.
Okay, cool.
All right.
Well, I think I have no more questions as of right now, but
Okay.
I'm going to attend your office hours. I think the only problem is I think I have my class ends at like 2:45. So
It ends then?
yeah, it ends.
Oh,
then.
okay.
So and I want to get somewhere comfortable, you know. I could do
Yeah, I understand.
I could sit anywhere. Is there any way that you might be able to extend it for like another 30 minutes if I have a lot of questions, or is it an hour?
Most likely. I don't want to promise that, but most likely.
Okay. Cool. Thank you, Professor. I appreciate it.
Yeah, no problem.
Have a good night.
You too.
Yeah, I think it's time for me to leave too. So thank you so much.
All right, Tyler, no problem.
All right then, bye.
I'm looking at the review questions right now, and I'm the last one. Okay, so I'll probably bounce and I'll let you go. But
Are you sure?
Yeah. I don't really have any questions. The one thing that I was wondering about is that it seems like they only have odd numbers. Is that correct?
You mean in the back of the book?
In the textbook, yeah.
They only have odd numbered answers. Yeah. That's right.
Oh, am I in the wrong place then? Okay, so I might be in the
No.
wrong place in my textbook. I have an online textbook, so I've been and I haven't really been using it, so I might be in the wrong.
Yeah, I mean,
place.
there's not a ton of reason to use it. So like you're looking at the exercises section and there's only,
Yeah.
if you're looking at the answers, that makes sense that you're only seeing odd numbers.
Okay. Yeah, that might be it. Let me go through and find that. If not, I might have gotten the wrong textbook and just realized it now, which would be
I
unfortunate.
doubt that's the case. But yeah, keep me posted if you if that's really strange.
Yeah, okay. I'll figure this out later. I think I should be all right for now, and I'll again like shoot you an email if something horrible goes wrong, but like I
Okay,
can
sounds-
do it probably on my
sounds good.
phone. Thank you so much.
Yeah, of course.
Have a good night.
You too.